So last time we started discussing the computational complexity, the computational complexity of learning. And after some discussions, we came to the conclusion that what we have to look at is that estimate the computational complexity as O of a function of 1 over epsilon, 1 over delta, and some complexity parameters. So the O of just says that we don't care about constants, and we really look at the asymptotic behavior. And here asymptotic could be with any of these parameters going to infinity. And the runtime, or the number of steps that we count, we just count computation steps. And we allow them to be any algebraic operations over real numbers. What we care about is how it behaves as a function of the required parameters of success of the learner, and which could be some complexity term. And we will see in examples that it could be different things. So you explicitly say what complexity term can you now, you're now analyzing the runtime with respect to. So that was the first conclusion. There was also this subtle point that we need the output to be a function that's easily computable to prevent cheating. And our first example, so what we will start today is with seeing some examples. Our first example of analyzing the computational complexity of some learning task was the task of learning axis aligned rectangles in some Euclidean space, say Rd. So we wanted to analyze in this respect the complexity where my parameter here is going to be d, which is a good parameter for the complexity of learning such a thing. I mean, what does it mean to learn rectangles in Rd? It means that if, say in the papaya examples, you say I have the papaya, and I have here color, and I have here softness, and I'm trying to predict whether the papaya is tasty or not tasty by a rectangle in these two parameters. Now, what does it mean to make my predictor more complex or more expressible? I could add another direction. I could say it's not just a matter of the color and the softness of the papaya, it's also a matter of the size of the papaya. I somehow believe that smaller ones are more tasty than bigger ones. Or I could add another coordinate and say it's not just a matter of color, softness, and size, but also of symmetry. If they look very round and symmetric, maybe they are tastier than whatever. So by adding more parameters, I make my hypothesis class more expressible. I can take into account more variables. But it also makes sense that now, to learn this most expressible class, I will need more time. So that this d that I'm using here now as my complexity parameter is somehow a good measure of how elaborate do I allow my assumption to be. And that's important for learning, because when we are doing agnostic learning, we are just comparing ourselves to the best in the class. So it will be easier to find something which is as good as the best prediction that you could do just based on two variables. It's harder to do as best as the best predictor based on 10 variables. So it makes sense that I will give you more time when you're competing with a more expressive class. Okay, so this is our first example, running rectangles in Rn. And then we wanted to give some kind of a positive result. And upper bound on the complexity of learning. So we had a positive result, and it consisted of 2 steps. So to prove a positive result, positive means it can be learned under such time bound, we need 2 steps. I mean, it's not the only way to do it, but that's a very kind of a mainstream way to do it. Step 1 is upper bound the needed upper bound the needed sample size. Right? So you get these parameters. What is the epsilon you're shooting for? What is the delta you're shooting for? And in what space are you working? And you want to tell us how much time you will need for this learning. So the first thing you want to upper bound the sample size, and we do it by our basic fundamental result. We know that the VC dimension of this class. So let's give this class a name. So the VC dimension of this class, rectangle in our D, we know that it is 2D. And therefore, in order to achieve these parameters, we need the sample size M of H of rect D. We know for epsilon delta, we know by the fundamental theorem that it is bounded by some constant times the VC dimension. So the VC dimension here is 2D plus ln 2 over delta divided by epsilon square. So this is the fundamental result that tells us the sample complexity bound as a function of the VC dimension. So we know that if we want to learn rectangles to such precision, we could just do ERM over this size of a sample. So that was step 1. Estimate upper bound the size of a sample that you will need for this type of learning. Step 2 is the computational side, part. Now that we know what is the minimum sample size that we are going to need, the question is how much time we need to process this sample size. So step 2, upper bound the time needed to compute ERM of this class of rectangles in D dimension over M. This is over a sample size of size M. How much time do I need to compute the ERM over such a sample size? And then we will just substitute the M for the sample size that we need. Okay? So now, in order to do this, we have to propose an algorithm and analyze the runtime of the algorithm. So this was the algorithm that we suggested. So here is an algorithm for doing it, for just carrying out this task. And the algorithm does as follows. So let A1 up to A, so let's put some AT here, up to M to the power 2D be a list of all subsets of S of size 2D. So we get a sample of size M, and I make a list of all the subsets of the sample size that have size 2D. So there are going to be m to the 2d such subsets. If I allow repetitions, it's exactly m to the 2d. Any questions at this point? Because to pick a subset of size 2D, I have to pick the first element, I have m options. I have to pick the second element, I have m options. I have to pick 2D elements. For each of them, I have m options if I allow repetitions. So in total, I have m to the 2D. OK, so I prepare such a list. And now I describe the algorithm for. So the algorithm has step A for t between 1 and m to the 2d. Let RT be the minimum axis aligned rectangle that contains 80. So 80 is a set of 2D sample points. And if I get a subset of sample points, I can look at the minimum axis-aligned rectangles that contain all of these points. That's well defined. I have a collection of some 2D points, and I ask what is the minimum rectangle. So in each coordinate, I move it until I hit one of the points. And this is the minimum axis-aligned rectangles that contains all of those points. It could be other points inside. So this is a well-defined step. I give you a subset of size 2D. You give me the minimum size rectangle the minimum rectangle that contains all of those points. And once you calculated this rectangle, I also ask you to calculate and compute LS of this RT. So I ask you to compute the sample error of this rectangle, which is just, I have my sample. You see, I have my sample, which is lots of points. And they are labeled plus or minus, plus or minus. And now I picked some rectangle. This is my rectangle RT. So I can compute its empirical error. I just count how many pluses are outside, how many minuses are inside, and divide by m. So I compute this loss for every such rectangle. And finally, what would the output be? So I run this for all the rectangles. And now, what do I output? I'm trying to find the ERM rectangle. So what should I output? Yes? The one that has the smallest error. Just output some AT that belongs to arg min of the LS of AI. One with the smallest sample error, right? The arg min says the one that minimizes this quantity. So clearly, this gives me the minimum error rectangle among all the rectangles that are supported by 2D points. Yeah, I see questions. Yes?
Are we outputting the arc, the rectangle, not the set that gave us the lowest? So
no, the rectangle. The rectangle is going to be your hypothesis.
Right, it looks like we interchanged AT and RT.
Oh, RT, OK. Yeah, this is all RT. OK, you're right. This is all the yeah, sure. But you didn't email me last time.
So I accidentally saved as a draft, but I sent it right before this class.
OK. Because
I'll be faster with this one.
I mean, they expire, you know. Right. So we output the rectangle. So clearly what I got here is the minimum rectangle among all those that are defined by 2D points. But I claim that this is also the minimum rectangle in terms of error, the minimum error rectangle over all possible rectangles. So the only thing I need to claim is, so I have here when we describe an algorithm to do some task, we know it from algorithms, we have to prove two things. I mean, we have to estimate the running time of our algorithm, and what else do we need to do? Correctness. So what is the correctness here? I have to show you that I'm really getting an ERM rectangle, right? So correctness for correctness, all I'm saying is that for every h in my class of rectangle over dimension D, there exists for every such h, and this is for every s, there exists some RT in my list such that LS of RT is less or equal LS of this H. So what I'm saying, although the class itself is infinite, there are infinitely many possible rectangles. For every rectangle, given a sample, for every rectangle, there is one of the rectangles in my list, T between 1 and m to the 2D, that has a small error as this arbitrary rectangle. And the reason is that if, say, this was the minimum error rectangle, I could always shrink it until it touches at most D points. And then the resulting rectangle has the same empirical error because when I shrank it, I didn't cross any point. So any point didn't change its labeling. So the empirical error did not change. And the new rectangle, so that was my original H, that was supposed to be the minimum risk rectangle. And this is some RT, because it touches point from the sample. So for any H, there is an RT in my list that has the same error. And therefore, for every H, I can, if I minimize the error over all RTs, I really got an error minimizer over all H's. So that's as far as correctness goes. Any questions about that one? Yes?
Why do we allow for duplicates? Wouldn't it be just as easy to like choose M, choose 2D?
Yeah, I could do M choose 2D. I allowed duplicates just to not to have to worry about justifying this bound. Because last time people were asking me about this bound, and I felt, why get into combinatorics when it doesn't hurt me not to? So we have correctness. Any other questions about the correctness? Yes?
Can we generally just say that since RTs shatter a sample, then since rectangles shatter our sample?
The rectangles don't shatter our sample. Because the sample could be, you see, the sample is much bigger. So you look at this, this is the sample size that we are picking. The biggest set that we can shatter is of size 2D. Now we're picking a sample of this size. Say epsilon is 0.1. So it's 100 times the size of a shattered set. Right? Because you divide by 0.1 square, you divide by 0.01, you multiply it by 100. So the biggest set that you can shatter is of size 2D, but you picked a much bigger sample. We know if you biggest set that you, this is the visit dimension. That's the size of the biggest set that you can shatter. the sample size is by a factor of 1 over epsilon square bigger. Okay? So we have correctness, and now we want to do a runtime analysis. So what is the runtime of my algorithm? So the runtime of my algorithm, we know that we have m to the 2d many steps here. And the question is, what is the cost of a step? So what do you think is the cost of one step here? Yes? I think it's O of m, because the expensive part here is computing the loss. I have to compute the loss over S. So I have to go over all points of S and mark, is this point labeled correctly or incorrectly? Because I have to count how many errors over S do I make. So I have to go over the sample, and for every point, I have a rectangle. I'm going over all members of my sample and check for each of them whether this rectangle gives us the correct label or not the correct label. So these steps take me one run over my sample. So each step takes me time m. And I have m to the 2d many steps. So my sample size is roughly, runtime is roughly m to the 2d plus 1. But of course, this is not in terms of the parameters that I want for my runtime. So in order to get this bound in terms of the parameters I care about, I have to just substitute this for m. So in terms of the parameters that we care about, I just substitute this for m. This m is mh, and I get runtime, which is some constant times 2d plus ln 1 over delta divided by epsilon square, all of this to the power 2d plus 1. So that's the bound that I got. Yes? I have a constant here. I have this constant just to save me from all questions about log versus ln and 2's in all kind of places and so on. So this guy, he protects me. So if I look at this runtime, what do I see? I see that if I fix d, if I view d as constant, I just want to learn rectangles over 5 variables, then these things look like polynomial time. Because if I have 5 variables, I have here my parameters, 1 over epsilon, 1 over delta, and the power here is 11. So it's 1 over epsilon, 1 over delta, to the power, it looks like 1 over epsilon to the power 22 times log 1 over delta to the power 11, something like that. It's definitely polynomial in 1 over epsilon and 1 over delta. If I ask myself whether it's also polynomial in D, then it isn't. It's exponential in D. So it's really a question of what is the complexity parameter that I allow myself to depend on. If I want an algorithm that scales nicely with the number of parameters, then I'm not polynomial. Now you can ask, the next question you can ask, can we have a better algorithm that will be polynomial in D? That's a very natural question to ask. And the answer is no. Oh, you know that the answer is no? I mean, I worked very hard to publish a paper about this, I don't know what, 20 years ago, but he just looks at me and knows the answer. I mean, yeah. Anyway, we can prove that unless p equals np, you cannot get rid of the exponential dependence on D. I will talk about it a little bit more later. Now what I want to focus is on the positive result. We'll talk about negative results later. Okay, so this is our first example of a positive runtime result for learning. We know what are the parameters that we are looking at, and we have some kind of a paradigm of how to analyze a learning problem. Analyze the sample complexity, find a way to do ERM as efficiently as possible. Notice that this ERM was not completely trivial, because initially ERM is go over all h's in your class and estimate the error of each of them, and we had infinitely many h's. So we needed some kind of an insight here to say it's enough to go over only rectangles that are determined by at most 2D points. OK, so this is our first example. Now I want to give some other examples to show you that things can behave a little bit differently. So our next example. So in the next example here, my domain was the Euclidean space. Now my domain is going to be the Boolean cube. So here my x is going to be the Boolean cube that is the set of all vectors, all 0, 1 vectors of length d. Now sometimes, the papaya is a good example of a learning problem where we have the natural modeling is over Euclidean space. But there are learning examples in which the natural modeling is over a discrete space. For example, if every variable just can get the label yes or no. Say I'm trying to do spam detection. So now the features of an email are just, I can say, I'll have some words that I care about, and I'll just mark whether the word occurs there or does not occur in the email. So every email will be represented by a vector of occur, not occur, over the set of keywords that I'm going to use in order to detect spam. So every email is going to be represented as a vector, as a discrete vector like this, which we also call the Boolean cube. OK? So now this is, and we want to learn over the Boolean cube. Now, rectangles may be a very natural class over the Euclidean space. Over the Boolean cube, one of the most natural classes, so now I have to tell you which class I want to learn. So consider the class of conjunctions. So let H con D be the class of Boolean conjunctions over 0, 1 to the D. So what do I mean by Boolean conjunctions? So we have to talk a little bit about propositional logic. So I have variables. We consider variables. Consider the variables P1 up to PD. So this could be, does the word, I don't know what, $1 million occur in my email or not? Does the word sex occur in my email or not? Does the word, I don't know what, earn occur in my email or not? Is it all capitalized or not? So these are my variables. And now we have a notion of a literal. A literal is a variable or its negation. So a literal could be either pi is a literal or not pj is a literal. These are literals. So how many literals do I have over n variables? Over d variables, how many literals do I have? Yeah, 2d literals. And then I move to the next step and I say what is a conjunction. So a conjunction is a formula of the form and, or let me write it, it's like L1 and L2 and Lk, where each Li is a literal. Yes?
Is P, so a literal is a variable and the negation is the same variable?
Either a variable is a literal, pi is a variable and not pi is a, there are two literals generated by each variable.
Okay.
Each variable generates two literals, itself and its negation. Right? So why is this a class of natural things? I can say that I will mark email as spam if it has the word sex and it doesn't have my first name and it does have capitalized words and it does not have any personal information about it. So I have a list of ends, conditions, that if all of them are satisfied, then I will classify the email as a spam. And each condition relates to some variable, whether the variable should be with value plus or with value minus. So it's a very natural class to consider for doing predictions over the Boolean cube. I can now rewrite conjunctions. I can rewrite them as a big end of some Lij, where j goes from 1 to k. I mean, I pick k many literals, and I write it like this. The end of all those literals.
What is I?
What?
What is I there?
Lij is, I mean, okay, so assume that what I have here is L3 and L7 and L200. So I1 will be 3. I2 will be 7. That's the I is the J tells me where it is in my list, and Ij tells me the index of this literal. Okay? So here I1 equals 3, I2 equals 7, and Ik equals 200. So Ij is the index of the jth literal in my conjunction. Yes?
So J is like a subscript
J is a subscript on
on the I?
the I. Right. And now I want to learn this class. It's a very natural class. I mean, there are many real problems in which we are interested in such simple prediction rules. This is a very simple prediction rule. You just have a set of conditions, and you want what is the best set of conditions such that if all are met, you will accept. It's like, you know, the conditions for getting your degree. You have to fulfill this requirement, this requirement, this requirement, but also you have to satisfy some negative requirement. You were not convicted of any major crime or something. Okay, now we want to learn it, and we're going to do a very similar analysis to what we did before. So what is the complexity? The computational complexity. Sorry, we have to do something to distinguish these two, right? Of learning this class, which are called H con over D variables. And we're going to do this first, the same two steps. Step one, I want to estimate the sample size that I'm going to need. So step 1, we're going to consider ERM learning. We will later see that sometimes we can get better algorithms than ERM in terms of the time complexity. But for now, we are considering ERM learning. So the first step is to estimate step 1, upper bound MH for my class of epsilon delta. How many examples do I need in order to guarantee that ERM gives me epsilon delta learnability? So anybody has an idea how are we going to address it? Yes? Find the VC dimension, sure. So it's a good start. But now, how do we find the VC dimension of these guys? So at the beginning, it looks like, I asked you in the assignment to find the VC dimension of the also a class over the Boolean cube, the class of all parity functions. And probably you can attest that it's not trivial, right? It takes work. But here we can settle here for a loose upper bound. Because I don't care about the exact size. I just want to get what is the ball game that we are in. So what is a rough estimate, a rough upper bound of the VC dimension? As a rough upper bound of the VC dimension, we can always take log of the size of the class. Because my class here is going to be finite. Right? So recall that for any class H, VC dim of H is at most log of the size of H. So now we have to estimate how many conjunctions can we have, which sounds a little bit simpler than estimating VC dimension, just counting. So anybody has an idea of how to count? Yes?
I was going to say it's 2D because there's 2D literals, each one could or could not be in the conjunction.
OK, so there are 2D literals, and each of them could or could not be in the conjunction. So you get, that's nice. We can do a little bit better, but that's not bad. That's nice. So the claim here was that the size of H is at most 2 to the 2D. Why 2 to the 2D? Because I have 2D literals. Every variable generates 2 literals. And for each literals, I can just decide whether it is or it is not in my conjunction. Anybody can give me a little bit better bound? Yes? 3 to the D even, right. So we can even get a little bit better. I claim that H is even less than 3 to the D. Why 3 to the D?
Either you have the variable, its negation, or neither.
Right. So for every variable, here for every literal, I have 2D literals. For every literal, I decided whether I want to include it or not. In this suggestion, for every variable, I make one of 3 decisions. Include PI, include the negation of PI, or forget about PI. So I get a little bit better bound. So let's use this bound, but it really doesn't matter. OK, so the size is at most 3D, or this is 4 to the D. It's a little bit worse, but it's still a nice bound. And we know, so now we can bound the sample complexity. So MH of epsilon delta is going to be at most a constant time the VC dimension, but the VC dimension is at most the log of this guy. So somehow it's easier to take the log of this guy, right? So the log of D is 2D, but I can just put D here because I have the C. plus log or ln 1 over delta divided by epsilon square. So I got this by just taking the log of this guy. OK, so this is a good start. I know that my sample size is polynomial in 1 over epsilon 1 over delta. If the sample size that I need is not polynomial in 1 over epsilon 1 over delta, ERM will have to somehow manage without looking at all the samples, which is going to be very difficult. Yes?
Why is it 2D there and not 3 to the D?
Oh, because I took the log of this. The log of this is 2D. The log of this is a little bit less, is d log 3. Log 3 is less than 2.
Oh, right.
Yeah, just put it in the constant. OK, but now we know what is the sample size. We need to go to step 2. Step 2, given a sample S of size any m, how much time do we need, or computation is needed to compute ERM with respect to our class over this sample. Now note that again, if I do brute force, if I go over all elements in my class and check the empirical loss of each of them, this is going to be pretty expensive. Because if I know that the size of the class is something like this. So if I go all over all of them, I may have to multiply this. I mean, I'll have to carry out. OK, just a second. OK, I'll need 3 to the d many steps. I can do better than this. I can do is a number of steps, which will be only polynomial in d. OK, so let's see what we're going to do. So here we have a nice, tricky algorithm that will save me this problem of running over big number of h's. And the algorithm is like this. So the algorithm runs in iterations. So we define a sequence. So here is a recursive formula. So let H0 be the full conjunction. So H0 will be the conjunction of all possible literals. So it's going to be Pi and P1 and not P1 and P2 and not P2 and PD and not PD. So this is what I have here is all 2D literals. Now, what can you tell me about this hypothesis? How does it classify a given Boolean vector? You get a Boolean vector, zeros and ones. How will this guy classify it? False. It's always false. No matter what happens. I mean, even just looking at these two, I know that it will always output false. Yes?
So is this still a conjunction?
Why not?
Is this, well, because we said in the bound 3 to the power of d, right? So we can either include nothing, P1 or not P1. So we can include P1 and not P1. So it's 4 possibilities.
Right, right. So it's true that in this bound, what he's saying, oh, I cheated this bound. But yeah, in this bound, we kind of used the knowledge that there's no point in including both P and not P. Because it gives me the zero, the all false conjecture. I don't have to repeat it P1 and not P1, P2 and not P2, they're all the same. So that was kind of a redundancy knowledge that I took into account with this calculation. But formally, any conjunction is a legitimate hypothesis. Although it's very redundant, and instead of writing all of this, I could have just written this guy. OK, and now we are going to define a process on which we go and improve our hypothesis. Because this hypothesis over the sample, what is going to be LS of this hypothesis? What is going to be LS of H0? How many errors it is going to be, it's going to make over a sample? What? I can't make an error. This guy will always predict 0. So how many errors do I make? Yes? Right. It's just the number, the set of all xi, yi, such that yi equals 1, divided by m. Whenever the label is positive, I'll make an arrow. Whenever the label is negative, this guy just tells me negative on everybody, so he is not making a mistake. So that's the first. Now the question is, how do we proceed? So given ht, we define ht plus 1 as follows. So now we consider the t plus 1s, or the t's example in S. So this is some xt, yt. And now there are two cases. I want to decide what is ht plus 1. So I'll have two cases. One case is if ht of xt equals yt. I check my current hypothesis on the tth example. If it predicts correctly, that's a very general rule. If it works, don't change it. So if it predicts correctly, ht plus 1 will be ht. Now, if ht of xt is not equal yt, what do you suggest that I will do? Now we have to remember, how are we making the progress? We start with making all kind of requirements. I'm starting by making the requirements, in order to become a student here, you have to be tall and you have to be short. You have to be smart and you have to be stupid. You have to be rich and you have to be poor. OK, nobody can satisfy all these requirements. Now I have some list of current requirements. And there comes a student. And this is a student I really want to accept. So I'm going to tweak my requirements. How am I going to tweak my requirements to accept this student? I'm going to delete any requirement that this student doesn't satisfy, so that my next requirement will be such that the student is really inside. So if I have an example on which I make a mistake, note that we make only mistakes on examples that are labeled 1. Examples that are labeled 0, we already rejected everybody. We are very tough. So there comes someone with label 1, and we make a mistake. That means our current example is going to reject it. So what I'm going to do is delete from ht any literal. So let's continue here. Any literal that has a conflict with xt, yt. In other words, what is xt? Xt is a vector. Xt is some vector. 0, 1, 0, 0, 0, 1, and so on. And I have literals in my requirements. So I wanted to satisfy the requirements. So if I had here not P1, I'm happy. This is 0, and I had not P1. If I had here P2, I'm happy. It requires 1, and the guy has 1. But assume that here I had P4, but on the fourth coordinate, this guy is 0. And the requirement P4 would have then rejected it, because it doesn't satisfy the requirement. So what I'm going to do is just delete this literal. So this is a bad requirement. It rejects someone that I wanted to accept. So I take ht, and I delete all the literals that contradict the current example that I know is labeled 1. So in other words, ht plus 1 is the minimal conjunction that accepts all the plus labeled examples among x1, y1 up to xt, yt. So at step t, I make sure that I'm doing well on the first t examples. And each time I'm taking the minimum, I'm just taking the most demanding. It's not the minimal conjunction, it's the, say, write it like this, the most demanding conjunction that accepts everything that's labeled plus so far. Right? So what will happen when I get hm? When after m steps, hm plus 1, hm plus 1 is consistent with S. I mean, this is assuming what? Yes?
None of the negative examples start passing?
What do you say?
You say HM plus 1 is consistent with S. All the positive examples will,
All the positive examples will pass.
but the negatives might start passing.
Right, but how? Okay, so how do I guarantee that negatives don't start passing? I have to add an assumption here. Yes?
You assume that all of the, like, that S only contains unique ones.
Not unique ones, but this is assuming
Or, I guess,
some conjunction has 0 error over S. Because I have the most demanding one that accepts all the ones. So if I want to accept all the ones, I cannot make more requirements. But if those requirements still let some zeros go through, it means that I cannot at the same time accept all the ones and reject all the zeros. So here, remember that in the learning of rectangles, we didn't have to assume realizability. Here we get stuck. This algorithm will only work for the realizable case, if there is a conjunction that is consistent with S. So here we get an algorithm that only works in the realizable case. And we will see that often it is much easier to handle the realizable case than to handle the agnostic case, the general case. OK, so this was our correctness considerations. Now we have to do the runtime consideration. So this is correct in the realizable case. Now I have to do runtime assessment. What is my runtime? So I know that I had m rounds. And in each round, I only had to examine one example and see if it passes the conjunction. So it's something to see if the example passes the conjunction. I have to go over all coordinates of the example and all guys of the conjunction and check them. So it's something like 2D. Now we substitute here mh of epsilon delta. So I substitute mh of epsilon delta where I have it. I did have it on the board somewhere. Right? So I get here the mh of epsilon delta is something like constant times 2d plus ln 1 over delta divided by epsilon square, all this times 2d. So now I got something which is polynomial in 1 over epsilon, polynomial in 1 over delta, and also polynomial in my parameter d. So I can, in the realizable case for conjunctions, I get an even nicer result. I'm polynomial also in my complexity parameter, which is the number of variables, or the number of coordinates. Yes?
If it's realizable, can't you use the upper bound for pack instead of the agnostic pack and make it epsilon?
Oh, I can save the epsilon, right. If it's realizable, it's a good point. If it's realizable, I don't even need the epsilon square because I know that the sample size is only epsilon and not epsilon square. So it's not just polynomial, it's even more polynomial. Right. Good point. Yes?
Where did the 2D come from?
What?
Where did the 2D come from?
Oh, the 2D comes because at each step, you have to take your current hi and see how many conflicts do you get with the example. Well, at each step, you get your h, and you get an example and the label. And you want to know which of those literals conflict with the example. So you have to go over all those literals, maybe 2D of them. OK, so we have two examples now. We saw that rectangles in our D can be learned in time, which is polynomial in 1 over epsilon, 1 over delta, but exponential in D. But that was the agnostic case. For the conjunction, we got even something nicer, polynomial in D, but it was only for the realizable case. What is happening? What happens in the conjunctions with the agnostic case? Boom, becomes NP-hard again. So lots of stuff becomes NP-hard. But we will talk about it a bit later. Yes?
What does the realizable case mean again?
Realizable case means that the data generating distribution is such that there is someone in your class that makes 0 error. You don't, it's not that you're trying to minimize the error. You know that you can get error 0 if you just go over all members of your class. And we used it in our algorithm. So I still want to show you another example because so far we've been doing everything with ERM. And I want to show you a situation in which ERM fails but another algorithm succeeds. Now, we know that if ERM fails and another algorithm succeeds, it kind of contradicts our fundamental theorem, right? How can this happen? In what sense can ERM fail and still another algorithm succeed? Yes? Right, computational complexity. It could be that carrying out ERM is computationally infeasible. Sample size ERM is as good as it gets. But computational, I want to show you an example where ERM fails, but another algorithm can be faster. And it's important because this is a really crucial consideration when you're trying to do real machine learning in life. So my next example is another class, a little bit more complicated. Example 3. Again, x is going to be 0, 1 to the d, but this time I will allow more complex formulas. I'll allow the class of h is going to be the class of 3-term DNFs over x. So what do I mean by 3-term DNF? Every h will look like each h in h has the form h equals a1 or a2 or a3, where each ai is a conjunction. So now I allow more flexibility. Now, before I said in order to be accepted to my program, you have to be smart and rich and good looking. Now I'm saying, okay, you're either smart and rich or good looking, or I know your father. So I have here other options of getting accepted. Yes? No, the 3 goes for the 3 terms. So I have 3 conjunctions. That's what the 3 is coming from. Each AI is a conjunction. Yes?
So typically that example had the problem where it's like, or I know your father, and you would need something else because it has to be a conjunction, or can one literal on its own be considered?
One literal on its own is a conjunction.
It's kind of like ended with one.
Yeah, but our definition of conjunctions will just can be of any length. It could also be of length 0. It said no requirements whatsoever. So this is, but again, we can easily see that this could make sense in reality. I have 3 passes into my program. Either to complete your studies, either you took all of this chain of courses, or you did that, or you did some community service or something. Okay? So we are considering this class. Again, we can do the usual stuff, look at the visit dimension. What can we say about this first step is, if you want to do ERM, the first step for ERM is estimating first step, estimating or upper bounding MH of epsilon delta. And for that, we have to somehow estimate the visit dimension. And we already have some kind of a very crude hammer that gives us some bound on the visit dimension. What is it going to be? The size, log size. Log size is a good estimate upper bound for the visit dimension. So what is the class? What is the size of this class of 3-term DNF over D? Anybody has a yes? What do you suggest?
3 to the power d cubed.
Right. We had to the 3 to the power of d before, so this is at most 3 to the power of d cube. Right? Because each of those I have 3 to the power, at most 3 to the power of d options of what to pick, and then I repeat this peak 3 times. So this is at most 3 to the power 3d. So we know that in terms of sample complexity, we are still polynomially known our parameters. So m h of epsilon delta is going to be at most this. Oh, are we polynomially known our parameters? Not really. Yeah. Take this. So we have here some constant d plus log ln 1 over delta over epsilon square, or just epsilon if you want to consider the realizable case. Because this is just the log of this guy, and all the constants are pushed into the C. So next step is how hard it is to carry out, to compute, or to compute ERM H of a sample S over an M size sample. And here comes a very kind of disappointing surprise. This is NP hard. This is too hard. This is NP hard, even in the realizable case. So I don't think I'll have time today to talk about NP hardness. Today I kind of devote it to positive results. Maybe next time we'll talk a little bit about negative results. But it turns out that now we cannot even carry it over the realizable case. So we are completely stuck. We are completely stuck unless we come up with another algorithm which is not ERM. So what can we do which is not ERM? I mean, I'm not expecting an answer from you because it's not something that we've seen before. So here is a non-ERM algorithm. And the non-ERM algorithm here is based on the following observation. That if I have such a 3 DNF formula, I can turn it into a conjunction in a different space. So now I'm just using the De Morgan's laws of AND and OR. AND and OR distribute over each other. So we just note that each H that equals A1 or A2 or A3 is equivalent to the formula H prime that will look like this. I'll have a big conjunction over all U that comes from A1, V that comes from A2, W that comes from A3 of U, O, V, O, W. I can just open the parentheses, right? If I have P1 and P2 or P7 and not P8, I can write it as just open the parentheses. P1 or P7 and P1 or not P8 and P2 or P7 and P2 or not P8. So I can write it as a big and, where at every term I get here a 3 size disjunction, a 3 size OR. Now, why does it help me? Yes? Right. So now the trick is that we are now turning it into learning disjunctions. So now I'm saying, into learning conjunctions. Conjunctions over 3 variables. So we define, so now define new variables. How many new variables do we need? Lots of new variables. I want that every guy like this will become a variable. So roughly I need, each of them has, how many variables do I need? How many such triples do I have over D literals? So over D literals, I have 2D literals, and I am looking at picking all triples of them. So I have 2D define new 2D cube literals, variables. So I have a variable x times xp u v will represent u or v or w, x times x u v w. So for every such triple of literals, I will have a new variable, x u v w. And now my formula H is equivalent to conjunctions over this bigger space. Right? But we can learn it in time polynomial in this number of variables. So such conjunctions can be learned in time polynomial in 1 over epsilon, 1 over delta, and this new number of variables, 8d cube. But this is polynomial in D. So how could we have done this cheating? On one hand I tell you it's NP hard. On the other hand I tell you, why NP hard? It's just polynomial in 8d cube. And to try to understand what we have done here is we have to notice that we wanted to learn the class of 3-term DNF over P1 up to PD. We showed that each of those actually can be viewed as a member of conjunctions over dimension 8d cube. But those conjunctions, not all of them correspond to 3-term DNFs. There are also conjunctions which are not 3-term DNF. So if we run our algorithm, we're going to output most likely some h prime here that is not a 3-term DNF. Because those big conjunctions can express more than just the 3-term DNFs. So I can output a conjunction that is not a 3-term DNF, but still it will do good prediction. It will make me 0 error if there was someone here that gave me 0 error. So I'm learning in a bigger class, in a bigger representation. And this is called, OK, so before I take questions, we are running out of time terribly. So this is called this is another distinction, and I'll have to get back to it next time. There is distinction between proper learning, when you have to output H in H, and unrestricted learning, when you can output any H. And we switched from ERM, that is always proper learning, ERM always gives you something in your class, to learning unrestricted, and it allows us to overcome the computational barrier. Just one comment. The other Shai, my co-author for the book, he likes to call it improper learning. I don't like this name so much because there's nothing improper about it. But that's his favorite term, and it could be in the book appears as sometimes as improper learning. So here is a distinction between having to output a class, someone in H, allowing you to output anything you want. It can save computation time. OK, so we'll talk about hardness next time. Thank you.